a method that is meant to be implemented on quantum computers, and more specifically, near-term quantum computers. I emphasize near term because I think it's worth pointing out that, as for all emerging technologies, near term could mean anything between 5 and 150 years. So please take that with a pinch of salt. But it is focused on trying to work on machines as early as possible. So just a bit more about my background. As Samantha said, I do quantum computing research at UCL, and I also work for a company called Rahko, which is focused on developing innovative methods for drug discovery. So obviously together, my work is very much focused on looking at quantum machine learning methods for molecular computation, and more specifically, these methods that look at applying these concepts to quantum computing. We also do a lot of research very similar to the type of work that Anatoly will be presenting in the next presentation, but obviously this is not the talk of it's not the focus of my talk today. So the plan for today, we will be first going through an overview of the VQE, the Variational Quantum Eigensolver. We'll go in slightly more details about the VQE stack, so looking at all the different components that composes the algorithms and so on, and there are many of them. After that, we will be looking at what are the key problems with these algorithms and what still needs to be resolved. And after that, we'll look at some of the recent research that my team and I have been working on, that is, if we have time, and we'll finish with some concluding remarks. I'm really sorry about the design of the navigator. It's just that I tried something new, so we'll see how that works. Before we get started, some shameless work placement. The reason why we talk about the Variational Quantum Eigensolver today is because yesterday we published a relatively thorough review about the method. So it's about 145 pages. I don't advise to read it all at once, but the first 15 to 20 pages should be about sort of introductory background. So I think it will be of interest to many people. All right, so let's get started with the VQE. So the Variational Quantum Eigensolver is a method which aims to compute the ground state of molecules, the ground state energy of molecules. So we'll start from a molecular conformation, and the objective is to learn the energy of that molecule, so the energy of that conformation. So you go from a specific system structure, and then you can compute energy. So on the right-hand side, you see an example of dissociation curve for H2, which has nothing to do with the molecule on the left, but it's just some pretty pictures. But basically, it gives you an idea of the objective of the method. And it does so by focusing on it's basically based on the variational principle. So those of you that are not aware, basically the idea of the variational principle is that if you look at the expectation value of a molecular Hamiltonian, it will always be higher than its ground state energy. So what you can do is that you can variationally optimize your electronic wave function up until you find the point where you have the lowest possible energy, and therefore you find the energy of your molecule, so the ground energy of your molecule. Of course, there are many applications of this throughout quantum chemistry, material science, and chemical engineering. It's a sort of one of the core metrics that we want to look for. So based on this, the variational quantum eigensolver problem is to minimize the expectation value of a Hamiltonian with respect to a parameterized wave function, electronic wave function. And we see already where the quantum computer will be useful is we can actually model these electronic wave functions on a register of qubits with a very efficient set of operations. And we'll talk about this a little bit later down the line. But clearly, this is where the advantage of the VQE is compared to sort of more conventional methods for computing ground state energies of molecules. We can also rewrite this as a weighted sum of different sort of operators within the Hamiltonian, as this is just a slightly more complicated equation, but it's really to illustrate the fact that the variational quantum eigensolver is a method that is called hybrid, and that it is split on a conventional computer and on a quantum computer to really try to ask as little as possible from the quantum machine and make sure that it can be applied sort of on machines which are not too big, that don't have too many qubits, or are not too noisy either. So we're going to go through it in sort of a slightly more intuitive way, I hope. So the way the VQE works is that you will start with your quantum register, so a bunch of qubits that are all initialized in a zero state or in a low energy state. And you will apply a series of quantum gates through quantum operations. So, quantum operations are the type of work that Frank is very much working on, is making sure they are reliable. So through quantum control. And so once you have applied all these operations, you find yourself in all of your qubits are showing all these nice quantum properties. So they're all entangled with one another, and they mimic the behavior of an electronic wave function. Once you have done this, you can just measure them, and obviously you will collapse the wave function to a specific measurements, and repeat this a certain number of times to get an expectation value for your state, and that gives you a model for the wave function. Now, what you can do is that you can compute the energy based on this electronic wave function that you model based on the circuit, and using a classical optimizer, you can try to guess better parameters for your quantum gates and your quantum circuits. And by guessing these, you will hopefully find a quantum circuit which produce a model of the electronic wave function, which is better at finding a lower energy for the Hamiltonian. You can repeat this iteratively until you find the lowest, or until you reach convergence. And you will find the lowest possible expectation value of your Hamiltonian, and you will converge to the ground state energy. So we're going to go through all of these steps in slightly more detail. Hopefully that gives you a sort of an intuitive understanding of how the process works. And by the way, this counts as quantum machine learning because you are effectively learning how to model quantum state on a quantum computer. So the first thing you need to do is the pre-processing. So this step is very much about preparing the problem. And as I said before, we will start with the construction of the Hamiltonian. So you will start with a confirmation for a molecule, a specific molecular structure, and sort of coordinates between atoms. And you will translate that into a mathematical problem. So usually we use a second quantized Hamiltonian, which is expressed in terms of fermionic operators, which are basically operators that dictates the behavior of electrons in the molecular structure. And there's a bunch of choices that are available here. For example, the chance of basis set. I mean, I'm sure many of you will be familiar with sort of orbital basis functions and so on. And this is quite critical throughout the process. Obviously, one key choice is that one key impact is the accuracy of the representation of the Hamiltonian. We want the Hamiltonian to be fairly an accurate representation of the molecule we're looking at. And also the number of qubits that will be later on required, because the largest the set of functions you're using to model your electronic wave function, the more qubits you will need. So it's an important step to begin with. Once we have sort of our problem constructed, we need to encode it into operators that the quantum computers can learn, and these usually are spin operators. So if you're familiar with the construction of fermionic operators, you know that by construction they anti-commute, which is not the case for spin operators, which are usually represented by Pauli matrices. So you know your Pauli X, Pauli Y, Pauli Z. Because they do not anti-commute, we need to produce specific operators with them, and they need to be constructed with specific forms of encodings. And these encodings must maintain the antisymmetry of the problem, because we're looking at sort of a fermionic wave function. And the one thing that we'll mostly care about is, in part of this encoding, is to find an encoding that creates sparse operators. And the reason why we want sparse operators, so operators which will be mostly composed of identity terms, is that it gives a lot of very beneficial features later on in the algorithms. So we'll be discussing these briefly. And so that allows us to rewrite the Hamiltonian into a weighted sum of Pauli operators. And right now we can already use this to try to solve our problem on a quantum computer. But there's another step that we can take, which is to group specific Pauli operators that are, for example, commute with each other so that we can measure them at the same time. So for example, you will find a small quantum circuit that when applied to, the first Pauli operator A or the second Pauli operator B, will basically map it to a specific single qubit measurement. So there's quite a lot of work involved in this. And what that allows you to do is to measure several Pauli strings or Pauli operators directly on the qubit register in one go. So you can do this for all your different Pauli operators, and that allows you to rewrite the Hamiltonian a second time. And here, the key questions are really sort of what is the minimum number of groups that we can create, because we really want to save as many measurements as possible. So we want to have as few operators to measure as possible. And the next very important question is, what is the cost of implementing this basis? Effectively, it's a basis rotation. So what is the cost of it? So there's two elements to the cost. The first one is how long it takes to find these rotations. And obviously this is done on a conventional computer. And the cost of actually implementing these rotations on the quantum computer prior to doing a measurement of an operator. And that is more, basically the size and depth of the quantum circuit that will be required to do so. So that allows us to rewrite, as I said, the Hamiltonian second time. And overall, what you get is starting from a specific construction of a molecule, specific structure of a molecule, you can find yourself with a mathematical representation of it that you can measure directly on a quantum computer. There's quite a few steps involved in this, but that is an efficient way of representing a specific problem on the quantum computer. So the next thing that we want to discuss in slightly more details is the optimization loop of the VQE. So the way it works is you will start with initial, as I mentioned before, you will start with an initial set of qubits, which will be initialized pretty much any way you want, although there are some recommended initialization, for example, the Hartree-Fock wave function. Each qubit will be representing the occupation state of an orbital. So if you have 1, that means that an electron is located in that specific orbital, and if you have a 0, that means that the orbital is empty. And so the Hartree-Fock wave function is usually very simple to implement on a quantum computer, because you just need to move whatever first qubits you have into state 1, and that allows you to sort of already provide a good approximation to the state that you want to produce, which is the ground state of the Hamiltonian you're looking at. The next step is to implement the quantum circuits, which is in general called ansatz. And this is basically a series of quantum gates, which are applied sort of to the quantum state to model the electronic wave function. So oftentimes this will be informed by sort of physical theory. So we'll adapt specific theories. One that is mostly used is couple cluster theory. So if you're familiar with couple cluster theory, we can actually implement, we can create a quantum circuit which mimics a version of it directly on the quantum computer to evolve the state to the ground state wave function. And the key thing that we'll be considering when looking at the creation of an ansatz is, well, first of all, can it provide an accurate description of the ground state wave function? So is it physically motivated? The second one is how many gates are required to produce that specific wave function? And finally, how many parameters we'll have in this specific ansatz? The reason being that the more parameters you have, the more parameters you have to learn. And so that obviously takes more time throughout the optimization process. Once we've done this, we can perform the measurements and the measurements of the state. And as you know, quantum computers are stochastic machines, so you never get a measurement with 100% certainty. So you need to repeat the experiment many times to get an expectation value. And one key question in I guess all of quantum machine learning applied to quantum computers at least is how to efficiently sample observables. And obviously that's a very important question as well in the Variational Quantum Eigensolver. Once we have sampled this, then we need to define on a rule to update our parameters. And usually this works the same way you would do in machine learning. So you'll pick an optimizer. Here I gave the example of gradient descent, although they are much better optimizers for the VQE that have been produced and developed. And based on that rules, you will obviously update your circuit parameters and start again the whole process over and over again until you reach convergence. And the key questions here are really, the same that they would be in machine learning in general. Is how quickly does your optimizer converge? So what is your convergence rate? And obviously that will depend on the problem you're looking at, but some optimizer will be better than others. And what is the cost of the optimization step? And this is quite important because the question is how many points do you need to sample to be able to compute a gradient, for example. So with this in mind, that should give you sort of an overview of how the VQE works, and that we can now move on to sort of the less optimistic part of the presentation, which are the open problems of the Variational Quantum Eigensolver. And it's worth noting that a lot of this problem applies to all the Variational Quantum algorithms, and obviously this is quite generally a problem for sort of near-term algorithms for quantum computer. The first one is so-called Barren plateaus. So the idea of a Barren plateau is that throughout your optimization, the gradients of your parameters, attached to your parameters, will vanish exponentially as the function of the problem size. So it's very similar to the type of problems you have in machine learning with the cost of the curse of dimensionality and so on, with a slight twist on the nature of it, that if your gradients sort of approaches zero exponentially, that means that finding the direction of the gradient becomes extremely difficult. And so you need to sample a lot more to get an accurate estimation of what the gradient is, which means that the cost of the optimization increases tremendously. So I can provide a small visual example of what that means. So this is, on the left, it is the expected energy landscape of one parameter. So if you change the parameter between minus pi and pi, you should vary the expectation value of your Hamiltonian periodically. But when you have Barren plateaus, or when you have a Barren plateau problem, this landscape changes to this sort of much narrower peak somewhere down the middle, and very flat, a very flat landscape everywhere else. So you can see very quickly that if I'm, for example, on this point here, I can assess a gradient and get an idea of where I am on the optimization landscape and progress towards the optimal point, which is the minimum on the curve. But if I'm located here, it's a lot more complicated because we have no idea where we are on the overall optimization landscape. So mathematically, basically, if I recall the optimization problem of the VQE, which is to minimize the energy with respect to a specific ansatz, we can formally define the Barren plateau problem like this. So this reads that the probability of the gradient of the energy with respect to parameter theta I is greater than an arbitrary number epsilon, is basically bound by a value which decreases exponentially in n the number of qubits in your system. So this is not particularly a good sign for variational quantum algorithms, because it means that optimization is not possible in a lot of cases. There's a number of drivers for this problem to happen, and it's been shown to happen in a number of situations. So the first one that is worth mentioning is the expressibility of the ansatz. So the expressibility of the ansatz basically means if you have a specific quantum circuit with parameters in it, the question is, which part of the total Hilbert space can this ansatz reach with variation of the parameters? And the more it can reach, and the more it will be subject to the Barren plateau problem. This is why we care about sort of very physically motivated quantum circuits, because they allow sort of restricting the span of the ansatz. The degree of entanglement as well has been shown to trigger the Barren plateau problem, and so again we'll try to avoid unnecessary entanglement in the wave function. The non-locality of the cross function. So remember a few slides before I was talking about the sparsity of the Pauli operators. Obviously, the locality is a function of the locality of your cross function. So locality of your Hamiltonian depends on the sparsity of these operators, and so obviously you will want that to be as local as possible. And it's the reason why you want to be as sparse as you possibly can. And finally, there is such thing called something called the noise-induced Barren plateau, which is related to quantum noise. So whenever quantum noise affects your algorithms, what happens is optimization also becomes very difficult. It slightly changes the profile that you have here on the right, because it also reduces the amplitude of the energy value that you can reach. But it's also very much related to the Barren plateau problem. So before I move on to something else, just a quick mention that there are a lot of methods that have been proposed to mitigate this problem, in particular on like very strategic initialization of parameters, or using specific type of means to construct your quantum circuit. These have all been shown to at least help with the Barren plateau problem, but at the moment there hasn't been sort of a very deep, large-scale study on whether or not the variational quantum eigensolver can be shielded away from this problem. And so I think this is probably a small gap in the research that would be interesting to investigate. The next problem, which is a fairly obvious one, is quantum noise. And obviously, like every quantum circuit, every quantum algorithm, the VQE is subject to it. There's a number of types of quantum noise that can affect the variational quantum eigensolver. Gate errors, so very, very much similar to what Frank was talking about, is failure in quantum control. Decoherence of your state, so basically your quantum register gets entangled with the environment, and you lose the information that you have on it, and just simply sampling noise, so not conducting enough experiments to get an accurate expectation value of the observable you're looking at. So variational algorithms have been shown to be resilient to specific type of noise. So if you just to follow up on this, if you imagine an error in quantum control on a specific gate, for example, if this error is systematic, well, in theory, the variational algorithm can learn this systematic bias and bypass it. Obviously, this is a very restricted type of errors, but it still shows that these methods are quite important for the quite relevant for near-term the quantum machines, which cannot use full-fledged error correction. Also, there is a bunch of methods which have been produced for mitigating these errors. So it's not error correction, which requires thousands and thousands of qubits, but rather methods which are hoped to be quite cheap in terms of quantum resources, and that can allow for at least some degree of corrections of the errors that result from the quantum computer. One type of method is to predict errors based on the noise of the machine. So one way you can do it is control the noise of your machine by increasing the strength of your pulse on the gates and so on, and then you fit the results and you try to estimate what a noiseless system, a noiseless measurement would look like. And another method is what's called state purification, which is basically using quantum operation to filter out basically quantum noise from your state. This usually requires quite a lot of additional quantum resources, however, so it remains quite challenging to implement. But just to give you an example of the impact of noise, this is a plot on one of our research. Each dot you see is an energy estimation using the variational quantum eigensolver. And obviously, the closer it is to the dotted line, the better the estimation is. The sort of yellow line, the upper line as well, dotted line, is an estimation on one of IBM's quantum computer without any error mitigation. And what you can see is with the error mitigation, we get much closer to the target sort of exact energy. And the difference that you see is what I was talking about sort of earlier, is the vanishing amplitude that results from noise in the quantum circuit. The last problem, very much not the least, is the measurement problem. So a lot of studies have pointed out that the variational quantum eigensolver requires an enormous amount of repetition of the experiment to be valid, basically to provide an answer. The interesting point of the VQE is that it trades off with a very long quantum circuit that you need for sort of more involved quantum methods, for very short quantum circuits, so requiring very, very few quantum resources. But it does require a lot of repetition of the experiment to get an accurate estimate of the expectation value you're looking at. And there are a few drivers for this bottleneck. The first one is, as I was mentioning a minute ago, is sampling noise. So this is just basically a statistical formula, and it's very well explained in the reference that you have here. But basically, the idea is if you want to measure an observable with a certain certainty, with a given certainty, you need to repeat your experiment 1 over that certainty squared a number of times, and obviously that can be quite a lot of measurements if you want to do a precise if you want to get a precise expectation value. The other thing is the number of operators that you will need to measure in your Hamiltonian. So obviously, as I mentioned before, the Hamiltonian is composed of a weighted sum of operators, and you cannot measure them separately. And the normal scaling of a molecular Hamiltonian is n to the 4th, because the sort of two-body interaction term is composed of 4 fermionic operators, and therefore you have a combination of each of them 4 times. But the grouping method I was mentioning as well are very good at reducing this number. So we can almost get it down to linear scaling and the number of qubits in your system. So it's not exactly n, it's slightly higher than this, but it still is very good improvement. And finally, for each of your gradients, you will need to, for each of your parameters, you will need to compute a gradient. And for example, in one of the ansatz, which is a paired unitary coupled cluster ansatz, with the citation here, you have n to the square parameters, and so therefore you will need 2 sample gradients for each of these. So in total, this gives you a scaling of n to the 3rd divided by your target precision squared for the total number of measurements that you will need to complete one iteration of the variational quantum eigensolver. These numbers don't mean much, to be honest. So we're just going to look at a small example right now. But before that, we're going to look at a benchmark. So the benchmark will be a chromium dimer, which uses an active space of 26 electrons on 26 molecular orbitals. So because we use because we're looking at spin orbitals, that would be 52 spin orbitals, and so 52 qubits. And that's just a pretty picture of chromium dimer. And this was suggested as a benchmark by the paper that is sourced here as being basically sort of a tipping point between what is feasible on a conventional machine and what will be relevant for quantum computers in the years and decades to come. So without further ado, we're just going to look at how much that would take to run on the Variational Quantum Eigensolver. So let's make a few assumptions. So first of all, we're using the ansatz that I talked about. The details don't really matter, but we've compiled the entire ansatz on 52 qubits, and we found that the number of layers is about 27,000. So to anyone that knows quantum noise about the rates of quantum noise, this must be absolutely terrifying. but it doesn't necessarily sound that bad. We estimate that we can do one gate or one layer of gates in about 100 nanoseconds, which is slightly optimistic, but actually it's far from being the most optimistic assumption we're making here. Some superconducting quantum computers are actually able to do that. We assume no noise, by the way, because that would make it more complicated. We want to be able to achieve what's called chemical precision. So that would require about 1 million shots for each estimation of an operator. The number of operators in the Hamiltonian is estimated to be about 850. And the number of parameters in the ansatz is around 170 parameters. So if you're good at multiplication, you can very much quickly see the problems here. But we're going to go through it. So let's have a look. So if you want to do a single shot, so basically you run your quantum circuit only once, this gives you a runtime of 3 milliseconds, which is pretty good. Obviously, we're assuming no noise and that everything works perfectly, but it still is quite encouraging. But if you expand this to look at an estimation of the entire Hamiltonian, that will take you 25 days. And if you want to compute gradients on every single one of your parameters for the Hamiltonian, this will take you 35 years. That's using a specific optimizer. We have another optimizer here just for an indication, which still brings you to 24 years, which is not exactly optimistic at this point, but it's not the full picture. And we're going to discuss that sort of very quickly now. Just a quick comment here is that this is just for one iteration of the Variational Quantum Eigensolver, so you need to repeat that probably hundreds of times before you get to convergence. But let's have a look at how this can be addressed. One example is, one advantage of the Variational Quantum Eigensolver is that it's very, very highly parallelizable. So a lot of the operations I just mentioned can be conducted on parallel sets of qubits that are placed one next to one another. So for example, your million measurements that we talked about earlier can be done on separate quantum computers. So let's have a look at what it would look like if we were to parallelize everything. So if you were to do a single shot, obviously you will use one set of qubit and it will take you 3 milliseconds as we discussed. But if you want to do one expectation value and you want to keep it to 3 milliseconds, you will need about 800 million sets of qubits, which is quite a lot. We'll talk about that very soon. And if you want to do a full iteration, you can do it in 0.5 seconds, but you'll need 2.5 billion QPUs. Obviously, you can do it even faster, but you will need even more QPUs. So obviously, 2.5 billion is quite a lot of quantum computers. But the truth is if we compare to the way CPUs are constructed today, it's not that disastrous. I mean, it's definitely not for tomorrow, but it's not extremely complicated. There's a few caveats to this analysis as well. Is obviously I'm not taking into account communication overheads and potential additional errors that could sort of affect the accuracy of this result. But what's very clear here is that parallelization is necessary for the future of a method like the Variational Quantum Eigensolver. And I think one question that one should ask is, compared to sort of other quantum methods that are out there and somewhat competing with the Variational Quantum Eigensolver, is it more challenging to build 1 million qubits on one chip or 2 billion chips with only 100 qubits on each? It's not a straightforward question. So I think this will be left for the hardware community to discuss. But it's very clear that in any case, for a method like the Variational Quantum Eigensolver to be a valid method, this question will need to be answered. So I just wanted to briefly, before we close, I just wanted to briefly talk about sort of the recent research that I've been doing with my team. And it's basically, we're working very much in adapting methods that exist in conventional quantum chemistry to quantum computing. And one of them is a complete active space self-consistent field. So basically the idea is that you start from a specific active space of orbitals for your molecule, and then you try to iteratively update it, as well as at the same time as you're updating your electronic wave function. So the way it works is that you start with an initial guess of your molecular orbitals that could be doing arbitrary fuck. You then select an active space, and from that you construct an initial estimate, an initial version of your Hamiltonian. From there you can minimize the energy wave function using your Variational Quantum Eigensolver. And what you can do is that you can just sample the reduced density matrix of your Hamiltonian, which can then be used to, on a traditional computer, you can just sample the gradients and update your Hamiltonian accordingly. Once you have a new Hamiltonian, you can just minimize the energy again and continue this loop over and over again until you reach convergence. And that should allow you, in theory, to give you sort of a better estimate of the ground state energy, better than you would get with arbitrary fork, or better than you would get with a simple VQE. And in particular, it also allows you to sort of shrink the size of the system you're looking at to get a better accuracy but with lower resources. So in particular, a lower number of qubits, which, as mentioned above, is a quite important factor. So in terms of results, so we have sampled, we've done some tests on IBM's quantum computers, and we have in particular sampled these reduced density matrices. And so these are sort of plots of the errors. What you see on the left is a noiseless simulation. So that's what should be the type of errors that should be expected just from sampling noise. And on the right, it's run on the quantum computer. And so as you can see is once you include error mitigation techniques, you get very close to what you would expect with simply the sampling noise, which is a very promising result. And obviously it doesn't take into account the cost of the error mitigation itself. But it still shows that the errors that occur on the quantum computer are still fairly predictable. And at least for small systems, it's something that at the moment we can handle. Whether or not it gives you an accurate enough result is a different question, but that's it. And in terms of the optimization itself, so each dot you see, you've seen that plot earlier. Each dot you see is a different cycle of this loop, and you can see that we converge very quickly to the energy the target energy that we're looking for. So I just wanted to close with a few concluding remarks as the time the presentation comes to an end. The first one is it's very clear that there's still a long way to go for methods like the Variational Quantum Eigensolver to be a relevant method to use in the context of quantum chemistry. But it's progressing quite fast. I think the first paper that was published on the Variational Quantum Eigensolver is from 2014. So we are sort of 7 years down, maybe 8 years down the line. And an enormous amount of progress has been made, both in the theory and on the hardware side. The measurement problem is the biggest hurdle. So what the community should focus on is very much trying to reduce the number of measurements required, but also focus on how we can implement large-scale parallelization, and most importantly, is it worth it? Is it worth focusing on building millions of quantum computers right next to one another to do parallel computation? Obviously, the Barren plateau and the quantum noise problems will be a problem that will be very relevant or will determine whether or not this method is worth pursuing. But it's also clear that at the moment, there are two fields that for now, we do not fully understand how they impact the accuracy and the results of a method like the Variational Quantum Eigensolver. And so, numerical simulations will be required in order to answer this question. And so in any case, among sort of the near-term method for quantum computing, so methods that do not need error correction or that do not need sort of millions of gates, it is very much among the most promising, and in particular because of the many applications that it could have, should it be proven to be valuable methods, in particular in things like drug discovery, chemical engineering, and material science. On that note, that closes my presentation. So please let me know if you have any questions.